Hey everybody, welcome to Chapter 16, Guided Problems. I'm going to just kind of walk you through, like I always do with these guided problems, these 4 problems that are kind of representative of what you'll see in the homework. So let me start by opening up the data in Excel. All right, so this is the independent school. Here's their data showing their enrollments for the past several years. So the first thing they want us to do is forecast the 2011 enrollment using a 4-period simple moving average. So to do that, I'm just going to say that this equals the average of the previous 4 years. 1, 2, 3, 4. It's that simple. And I'll make sure we're rounded to what it's asking for, 639 students. Then it wants us to calculate the mean absolute deviation, or the MAD. So the easiest way to do that is to just sort of follow the table format that's given to you in the book. And the table for this is on page, let's see, page 773. So this is our period. This is our actual enrollment. We're going to have our forecasted enrollment. We're going to have our forecasting error and our absolute forecasting error. So to do the forecast, just like we did it here for 2011, what we're going to have to do, in fact, I'm going to kind of remove this from the rest of the data so it doesn't look like it's part of what we're working with here, because this is actual and that's the forecast. So we can't do a forecast for period 1 because we need 4 periods of previous data to do a forecast. So we actually can't do a forecast until the 5th period. And that forecast is going to equal the average of the 4 preceding periods. Our forecasting error is going to be our actual minus our forecast. And our absolute forecasting error is going to equal the absolute value. Use ABS, that's the function in Excel for absolute value of the forecasting error. Now we have all those formulas in, we can just fill them down. You'll see actually if I went down one more line that there would be my forecast for 2011. And then to calculate the MAD, we just take the sum of the absolute forecasting error, and then we divide that by n, and n is the number of periods for which we have an actual and a forecast. So there's 4 of them, actually, for which we have actual forecast or absolute forecasting error. So n is 4. So we're going to say the sum of the absolute forecasting error divided by n, which is 4, gives us our MAD. And they're asking us to round to 2 decimal places. Then it wants us to forecast the enrollments using exponential smoothing, which is a little bit different, but it's going to use this same table. The data will be different. So to do this, we have to have the first year we don't have a forecast, so we just assume the forecast is the same as the actual. That's the standard convention. So that means our forecasting error is going to be the actual minus the forecast, which is 0. And our absolute forecasting error is also going to be 0. I like to represent these as just like a dash or something because they're not actually 0. They're more like we can't calculate them because we don't have the appropriate data, because this first year was an estimate. But going into the second year, now we're prepared to start to calculate this. So again, I suggest using the table from the book. This table is on page 777. So the formula for the forecast, which is on page 776, is that we'll take our forecast from the previous period and we'll add to that our alpha, which is given to us here, 0.4 times the actual from the previous period minus the forecast. Whoops, and I didn't close my parenthesis all the way. So you'll notice that each time you do this, that the forecast in the second period always comes out to be the same as the forecast in the first period. But now we'll have a forecasting error, right? The actual minus the forecast, which will mean we'll have an absolute value or an absolute forecasting error. Now that we have our formulas in there, we can just fill it down. This represents our 2011 forecast. And you'll see that the forecasting error, because we don't have an actual, is actually off, so we just delete those. So there's our forecast for 2011. This asks us to do it to the nearest integer, so 644. Then it's going to ask us to calculate the MAD. Again, we take the sum of the absolute forecasting error and then to find our MAD, we divide that by n. Again, n is the number of periods for which we actually have data. So 1, 2, 3, 4, 5, 6, 7. Round to 2 decimal places. Now in the past, whoops, I hit the wrong button there. I've had problems with Excel with Pearson not liking the rounding, so let's see what happens. Oh, it was fine on this one, so good. So that is the end of problem number 1. Let's move on to problem number 2. All right, here's question number 2, and so I've already got the Excel information downloaded, or whatever you want to call it, the data put over here into Excel. This is shows the average number of viewers in millions for each season of a popular television show. So they want us to forecast the next season, 2009, using a 3-period weighted average with weights of 3, 2, and 1, applying 3 to the most recent data and 1 to the oldest data. So again, we can't forecast until the 4th season because we need 3. Whoops. Trying to talk and type at the same time. 3 previous seasons data to do that forecast. So for a weighted moving average, you can see the table on page 775. And it looks just like the ones we've already used. So forecasting error and absolute forecasting error. So our forecast for the 4th period, or the 2003 year, is going to equal our weight of 3 times the actual of the previous period, plus our weight of 2 times the forecast of 2 periods before the previous period, plus our weight of 1 times the forecast of 3 periods before the previous period. And then we're going to divide all of this by the sum of the weights. So if we had a weight of 3 plus a weight of 2 plus a weight of 1 gives us a weight of 6. And that's how we forecast. So our forecasting error is simply going to be our actual minus our forecast. And our absolute forecasting error is going to be the absolute value of the forecasting error. Now that we have our formulas in, we can fill that down. Again, our forecasting error and absolute forecasting error won't work for 2009 because, well, there's no actual data for that year. There's our forecast for 2009. It wants us to do 1 decimal place, 25.8. So to calculate the mean absolute deviation, we take the sum of our absolute error, we divide that by n, which in this case is 6. Again, the number of periods for which we have an absolute forecasting error. Two decimal places. And there we go. All right. Next, they want us to forecast the average number of viewers using exponential smoothing with a trend adjustment. So this is going to be a little different than the others we've done, but a similar concept still. So I'm just going to take the data, bring it down here. And if you look at the table for this, for doing it with a trend adjustment, it's going to be on page 780 in your book. And so now we're going to have our smoothed forecast, our trend, that is different, our forecast with trend, which is called our FIT, and our absolute error. So again, just like we did with our exponential smoothing in the previous problem, our smooth forecast for the first period, because we don't have any data and we don't have previous data to rely on, we set to the same as our actual for that period. And our trend will set to 0 because we don't have enough data to calculate a trend yet. So that's just the standard convention. Our FIT is always equal to our smooth forecast plus the trend. And our absolute error is the absolute value of our actual minus our FIT. And that's always going to be 0 in that first year. And actually, it's not even really a 0. It's we didn't have the data to calculate it correctly, but it still means it comes out to 0. So in our second year, we can do a smooth forecast, and the forecast, remember, with exponential smoothing equals our, in this case, it's our forecast with trend from the previous year plus the alpha that's given to us in the problem. In this problem, it is 0.3 times the actual from the previous period minus the FIT from the previous period. So that's our smoothed forecast for this period. The formula for trend is our beta, which is given to us as 0.4, beta times our forecast from this period minus the forecast from the previous period. So what's the trend or change from period to period? Oops, I missed a parenthesis there. Then we take that and we add it to 1 plus, I'm sorry, 1 minus our beta times the trend from the previous period. You can see with all these formulas that it's easy to make a mistake. So sometimes you just have to do your best. And like that, when the trend looks a little weird, sometimes I have to go back and double check my math. So I'm going to do that and check my formula. And I'm glad I checked it because I did have an error. I did not put an extra parenthesis in here on my smooth forecast. I should have noticed that number looked unusually low. So now, because it should be the actual minus the FIT, and I had it as 0.3 times the actual minus the FIT. There we go. Now that number looks right. So our FIT for this period is going to equal our forecast plus trend. And our absolute error is going to equal the absolute value, the actual minus the FIT. Now I have all of the formulas in that I need. All I have to do is fill. So my 2009 forecast is going to be this number right here. And again, my error won't be right because there's no actual to work into it. And it asks us for 1 decimal place. Then it's going to ask us, of course, to calculate the MAD. Remember, this isn't good data on the first one because we didn't have enough data to do it. Sometimes it's better to represent it as a dash than as a 0. So we're going to take the sum of the absolute errors divided by the n. And in this case is 1, 2, 3, 4, 5, 6, 7, 8. And 2 decimal places. All right. Now it's probably going to ask us which one we think we have the most confidence. We're going to say the one with the lower MAD, which is the 3-period weighted moving average because it has a lower MAD. And that's the end of number 2. All right, here we are on number 3. This one we're going to be using like a regression. We learned how to use regression in the last chapter. So we're going to do a trend projection for this data. I've already exported the data to Excel. So the first thing we actually want to do is run some regression data. So we're going to go to our data, hit analysis, click on regression, hit OK, and then we're going to tell it we want to select our Y data, our X data, and then tell it where we want to put our regression table. So there's our data. The numbers we're really interested in here are the intercept and the variable. Okay, because we're just going to use the straight line formula when we're trying to predict the next period. So our forecast for 9 is going to be, is just going to use this formula where we're going to say this equals our intercept plus x, which in this case is 9, the number of the period, times the x variable. That's going to give us our forecast. And then to calculate the MAD, just like in the previous problems, we have to set up our little table. And our table for this one is on page 787. So we're going to have our forecast, our forecasting error, and our absolute forecasting error. So again, to do the forecast, the easiest way is just to set this up so Excel will do all the work for us. So So just like we did for forecast for 9, our forecast for period 1 would equal our intercept plus our period number times our x variable. Now the problem is if we leave our formula like this, when we try to fill it, it's going to move down. It'll look at the next cell below each time we fill down. So if we want to tell Excel to stay looking always at cell E28, which is our intercept here, we just put a $ in there, and now it will stay on E28. But for our period, we actually do want it to move down to the next cell each time when we fill. And then for our x variable, we want it to always look at E29, so we'll put that $, and that tells Excel don't move those cells down as the fill operation goes. So there's our forecast for period 1. We can fill that all the way down, calculate our forecast for each period. Our forecasting error is our actual demand minus our forecast, and our absolute is our absolute value of the forecasting error. Oops, I didn't put an equals. Now we can use the fill tool. We'll take the sum of those, and the sum of those divided by n gives us our MAD. 2 decimal places, 1.93. And that's it for question number 3. All right, here we go with question number 4. So I've already got the data over here in Excel. And so what we have to do here is we have to test for positive autocorrelation. And remember that autocorrelation, it's a big fancy sounding word. And all it means is that our residuals, which is another word for the error, we're testing to see if they're independent of each other, if the errors are independent, or if they're related to each other in some way. And so this is a mathematical way of testing for autocorrelation. Honestly, again, if you don't fully understand it, don't worry. I'll be honest, I don't fully understand all of the math behind these things. So, the first step is for us just to learn how to do the test. So I will show you how to do that. So the first thing we need to do is come up with a null and alternative hypothesis when we're doing autocorrelation. And so, first of all, negative autocorrelation is super rare, so we don't usually test for it. We're testing for positive autocorrelation. And you can see there's only 2 options that involve positive, so those 2 are out. And then what we typically do is our assumption, our null hypothesis, is that there is no positive autocorrelation, which means we're testing to see if there is positive autocorrelation. All right, so the next thing we have to do is calculate our Durbin-Watson statistic. So in order to do this, we actually have to go through the whole process of finding our forecast for each period. And then we'll find our residual, which is just our error between our actual and our forecast. So to find our forecast, we're going to have to do a regression analysis. So I'm going to go to Data. I'm going to go to Data Analysis, choose Regression, and hit OK. And then I'll make sure that my Y data and my X data are properly highlighted. And I'll tell it when I want to output it. And we'll hit OK. And then there will be our output. And so just like we did in the previous problem, we can now calculate our forecast by saying it equals our x-intercept plus our period times our x variable. I'm sorry, our y-intercept. So our y-intercept plus our period times our x variable. And again, to make it easy for us to fill, we're going to tell Excel, stay on E34 regardless of the fact that I'm filling down, and stay on E35, but we want A2 to roll to A3, A4, etc. as we fill. There's our forecast. And then our residual is just another word for the error. Sometimes it's actually denoted with an E. So in order to calculate the Durbin-Watson statistic, we need some data here. So the formula for the Durbin-Watson statistic is on page 790, and it is the sum of our E, which is our residual, minus the residual from the previous period squared, divided by the sum of the residual squared. So what we need to do is get our residual from the previous period. That's often put down as E t minus 1, and usually the t minus 1 is a subscript, but to make our life easy, we won't worry about doing subscripts. And all we're going to do is say this equals the ET minus 1 for period 2 is going to equal the residual for period 1. So again, the numerator of our Durbin-Watson statistic is that we need the sum of our residual minus our residual from the previous period squared. If we take all those and take the sum of them, that gives us the numerator for the Durbin-Watson statistic. And then we also need the E squared. So really this is E minus ET minus 1 squared, if we were going to put a heading on there. Our E squared is just the residual squared. And the sum of that is going to be our denominator for the D statistic. So our Durbin-Watson statistic D is going to equal 1.96. Then we're asked to identify our critical values. The critical values are pulled from a table. We know our alpha is 5 and our K, which is the other thing we're going to need for this problem, is 1. So K equals 1. Our N is 15. And this is for an alpha of 0.5. So here's our critical Durbin-Watson values: 1.08 the lower and 1.36 the upper. And then they'll ask us to evaluate it. And there's a handy little table for evaluating it on page 794 in the book, about 2/3 of the way down. In essence, if our D that we calculated, 1.96, is below the lower, then we reject our null hypothesis and we conclude that there is autocorrelation, positive autocorrelation present. If it's between the two, then we say it's an inconclusive test. And if it's above the upper, which is our case here, because ours is 1.96 and the upper is 1.36, if it's above the upper, then we fail to reject our null hypothesis, and we conclude that there is no positive autocorrelation present. And that is it. I hope this has been helpful to you, and I hope you have a great rest of the semester. There's not much left, so good luck.